This video is actually going to cover two topics, gravity and torque. So we covered this topic a little bit last year. We said that anything that has mass can exert a gravitational force. Now, the important thing to remember is this r represents a distance between the two masses, and this distance is measured from the center of each mass. So anytime you're trying to calculate, let's say, the force of gravity exerted by some planet, you have to use the radius of the planet if you're considering an object at the surface of that planet. Now, capital G will have a value of 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. Should have included the units there. Again, this equation is an example of an inverse square law. This is because the force decreases the further the two objects get from each other, and we'll see an example of what that means. Now, anytime that we've calculated gravitational force, we've always used mg. Well, now that we know that both of these equations are equal to our gravitational force, then we can actually set them equal to each other. Now, remember that mg is used to calculate the gravitational force acting on an object near a planet. In our case, or for the most part, we've used Earth. So when you set these equations equal to each other, one of the masses is the mass of the object, the other mass is the mass of the Earth. So when you set them equal to each other, only one of the masses will cancel out. And what you're left with is g, lowercase g, is equal to capital G times the mass of the Earth divided by our distance from the center of the Earth to the object squared. So this equation can be used to calculate the strength of the gravity field or the acceleration due to gravity, not just on Earth, but on any planet. Now, looking at the inverse square law, we can see that if we increase our distance, we're going to be rapidly decreasing our force. So again, this little chart helps us kind of see that a little bit better. If we are one distance away, then our force is very large. But again, as we double it or triple it or quadruple it, we start seeing these large decreases in our gravitational force. Now let's look at a couple of numeric examples. If you double the mass of the planet, then you double the gravitational force. Again, you want to practice doing these equations without having a lot of numbers available to you, but just tweaking the equation as is. So again, if you double one of the masses, you're going to double the gravitational force. You can also think of, because everything on top is being multiplied by each other, if I were to pull the two out in front, then my original gravitational force is going to be doubled. The next example says a planet doubles in radius. Again, because of that squared, if I put a 2 in for the r, and remember the 2 times r is what's being squared, then what I get is g m1 m2 over 4r squared, or my original equation is being decreased by a factor of 4. Now here on the left-hand side, we are calculating the strength of the gravitational field, or the acceleration due to gravity. Again, if you are doubling the mass of that planet, then you are doubling its gravitational strength. And again, if you double its radius, then you are reducing its gravitational strength by a factor of 4. Another example says a planet doubles its mass but shrinks to 1/3 of its original size. Now, remember that the distance is being squared. So here you can double its mass. And when you double its mass, you automatically double its gravitational force. But then when you reduce its radius by a factor of 3 and you square that bottom part, that means that the bottom part becomes 1 over 9r squared. Now, when you have a fraction down at the bottom, remember that you have to inverse it and multiply it. So that gives you a increase by a factor of 18. Our last example has changes happening to both planets. Now, one has its mass doubled while the other one has its mass tripled. There's also an increase in distance between them. Now, it's very common to be given this amount of information and asked for only one of the gravitational forces. But we know, because of Newton's third law, that they exert equal but opposite forces on each other. So the only difference between asking for the gravitational force on one planet versus another is just the direction that it points, but the magnitude will be the same. Our next topic in this video is torque. Now, torque was also covered last year. It is represented by a Greek letter tau, and it is the tendency of a force to rotate an object about an axis. So in this case, we're going to normally refer to it as our pivot point. Now, lever arm, which is going to be represented by an R, is going to be in meters, and it is the distance from the pivot point to the location where the force acts. Now, this equation actually comes from the cross product R cross F. Now, it's very similar to the dot product that we saw when we were talking about work, but this is a cross product. Now, dot products want the two components of this equation to be parallel to each other. So that's where we use that cosine. Cross products want our two components of this equation to be perpendicular to each other. So that's where the sine comes from. So this theta is going to be the angle between our lever arm and our force. So again, when you know that they are perpendicular to each other, then this sine of 90 will give us 1. So here we have three different situations: an angle of 0, an angle of 90, and an angle of theta. Now, when you have an angle of 0, what that means is you are applying a force that is parallel to your lever arm. It's like trying to open a door by pushing on the hinges. For an angle of 90, you're actually applying a force that is perpendicular to your lever arm. And when that happens, you actually achieve your greatest torque. Now, when you have an angle of theta, then you have to use the equation RF sine theta. Again, theta is the angle between your force and your lever arm. By convention, counterclockwise torques are positive and clockwise torques are negative. This is mainly used when you have several different forces acting on an object and you're trying to determine what direction it will turn. So forces that cause counterclockwise rotation will be positive, and forces that cause clockwise rotation are going to be negative torques. Now again, the goal for the torque equation is to get the two components perpendicular to each other. Now there's several different ways to do this. One, you can either make the force perpendicular to your lever arm or a component of the lever arm perpendicular to your force. And we'll see a little bit more of these examples in class. Similar to forces, torques have a version of their own for Newton's second law. That is, that the sum of the torques, when equal to 0, causes 0 rotation. Now, the only time when that will happen is when you have both counterclockwise and clockwise torques, meaning negative and positive torques. So when you add these two together and you get a sum of 0, then that means you have no rotation. So an easy way to calculate when an object will be in equilibrium is to set the clockwise torques and the counterclockwise torques equal to each other and then solve for whatever information you're being asked to solve for. In this example, you're asked to calculate what distance the 2-kilogram box should be located in order for this object to be in equilibrium. Again, you have this 2-kilogram box that is creating or has a gravitational force acting on it, and you have this 3-kilogram box that also has a gravitational force acting on it. And both of these, although they're acting downwards, they're actually acting in opposite directions. One is clockwise, one is counterclockwise. Now, because they're both acting perpendicular to the lever arm, then you don't have to worry about an angle here. So mg, again, your force, times your lever arm r, which is a distance away from our pivot at this point, is going to be equal to mg times r of the other object, and here you're trying to solve for r, which, given the information, comes out to be 1.5 meters.